Hey everyone, so in this session I'll take you through the formulas related to the SVM. In the earlier part I talked about what is the vector which is perpendicular to a given line ax plus by plus equal to 0, and corresponding to that what is the perpendicular distance from any point x0 y0 to a line x1 ax plus by plus equal to 0, right? So with that in mind, let's get started on this. So to recapitulate, what I told was, if this is a line, right, ax plus by plus equal to 0. Okay, so equation of the line or the vector which is perpendicular to this specific line would be ai cap plus bj cap. Okay, and ij cap is nothing but the perpendicular axis, right? Similarly, the perpendicular distance of any particular point x0 y0 from this line is nothing but ax0 plus by0 plus c divided by under root a square plus b square, right, is what I had proved earlier. So with that in mind, let's get started. Let me just create more space for myself. In this session, I will be working mostly with the matrix representation. So let's, for being consistent, we'll just transform a and b into a w1 and w2, right? So what we will say is, let's say, okay, for that matter, let's talk about, let's say these are 4 points, x4, x5, s6 and x7. Okay, so in support vector machine, first of all, understand what the support vectors are. Support vectors are those points, right, which are at the boundary of classification, right, or the decision. So let's say that, okay, this point is there which can be classified as +4. So let's say all these points, okay, in this particular region are +1, and all these points in this specific region are -1. Okay, so we are saying x4 is +1, x5 is +1, x6 is -1, x7 and -1. Okay, so again I'll redraw this. So if you look into this, x4, x5, s6, xn. Okay, so if you look into this, these points are nothing but the support vectors because they lie at the boundary of the classification, right? So what support vector, these are the support vectors, and the idea of support vector machine is to find a line, dividing line, which is equidistant, okay, from these two support vectors. All right, so what we are saying is this is specific distance, right, perpendicular distance from x4 to the line and the perpendicular distance from x6 to the separating line. These, let's call it as p, okay, and let's call it as p1 and p2. So p is nothing but p1 plus p2. All right, and what we are saying is we want this distance to be maximum. Okay, and the thing is the thing is, why do we consider it to be 1, right? Why do we want this to be maximum equidistant? So the reason is, let's assume the same points. Okay, so let's say this is x4, this is x5, this is x6 and this is xn. Okay, now let's see, this is x3, this is x4. Okay, so instead of the one which is equidistance from these two support vectors, let's say our decision boundary is this specific line, okay, which is very very close to x4. So the thing is, it is still classifies it correctly, right? So if you, let's say this is the equation of the line is w1 x1 plus w2 x2 plus c equal to 0. If we put the value of x4, that is w1 x4 plus w2 x4 plus c, right, this would still be fine, right? This would still be fine because it is greater than 0. If you put this x5 over here in this equation, this would still be fine because this would also be greater than 0. And if you put the equation value of x6, this would still be fine because this would say that, okay, this is negative, this would be some negative value, and this will also would be some negative value. So and essentially it is classifying fine even if it is very close, because if you put the value of x4 x5 in this, it would be greater or equal to 0. If you put the value of x6 in and x7 into this, it would be greater or equal to 0. But the problem arises, so let's say we are trying to find out what is the boundary, right? Is this the label of a point which is very close to this, right? Let's say this is a particular point which we want to find out. So it would classify it correctly, saying that, okay, it is +1. But imagine that this point which we had given, right, due to the real time scenario, etc., this point was corrupted. Instead of this point being located over here, let's say we found out that due to corruption in data, this actual point should have been over here, right? Instead of this point being over here, it should actually be being over here. But if you look into this classification boundary, right? So earlier it would have classified it to be +1, correct? But now it is classifying it to be -1, right? So this is, there is a flip in the decision. And why is it? Because it is very close to the support vector machine, support vector, right? This particular decision boundary. But imagine a scenario in which this would have been in between, okay, over here, right? So let's say this point is x4, x5, x6, x7. So let's say there was another point, okay, which was over here, right? All right, so let's say this point was over here in our case. Let's call it as x8. All right, and now due to corruption in data, we found out that this point should not have been over here, this point should have been over here, right? We are saying this, but you notice that despite the movement of point from here to here, this would still be greater than 0, because this line itself is w1 x1 plus w2 x2 plus equal to 0, right? This line is equal to 0. Okay, so any point in north of this would be greater than 0, any point to the south of this would be negative, right? Less than 0. So when we had considered a boundary as +1, so even when the point moved from here to here, right? Because there was corruption in data earlier, it was over here, but then we realized, okay, there's some error, this point should have been over here. Even if that is the case, with slight movement towards the left, this is still giving us the correct result, right? So this way it is more robust, right? This decision boundary, and therefore we say that we are not just happy with the decision boundary being w1 x1, right, plus w2 x2 plus c, right? It should be, what we want is, it should be something, yeah. So the idea was, if let me redraw this, so what, so that's clear, x4, x5, x6 and x7. So what I was saying is, just recapitulate, okay. So if the decision boundary is somewhere close to this x4 point, right, which, and a bit distant from x6, so let's say if earlier there was a point which is like this, then it would have classified it as greater than 0, and then let's say if the point moved due to some corruption, it moved over here, then it would have become minus, right? It was +1 over here, then it would become -1 over here. So this is not so robust. But if it is at the center, if this line is at the center of like this, so even if the point moved slightly from here to here, it would still be dictating correctly, right? It would still be saying that it is +1, because it would be greater than 0. So that's the entire point of having this decision boundary at the center of the support vector machines, right? So what we are saying is, if these are the two lines, right, support vectors 1, line passing through support vector 1 and support vector 2, so we want the decision boundary to be exactly in between these two, such that it is more robust. All right, so earlier we have talked about that, if again x4 x5, I think I should quickly learn as to how to erase and then come back to the same thing. I think I would be writing this indefinitely. So if this is support vector line crossing through support vector 1, right, support vector 2, and this is our desired line. So this is our decision boundary, which is w1 x1 plus w2 x2 plus c, okay, equal to 0. Right, this is our decision boundary. And these points are not just one point, are not just one specific number, it is x41, x42. Okay, so let me write it like this. X4 is nothing but, again we are talking in vector dimension, right? So this is x41 and x42. Okay, one point in x direction, one is another in y direction. Similarly, x5 is nothing but x51 and x52. Okay, so and so forth. So when I'm saying w1 x1, w2 x2 plus c equal to 0, it essentially means nothing but ax plus by plus c equal to 0. The only difference is in ax plus by plus c we considered x and y to be here perpendicular like this. In this scenario we are saying that okay, we are having x1 over here and x2 over here, right? And why I'm writing this, because I'll be writing in the matrix rotation, so this line becomes wtx. And how does that transform into w1 x1 plus w2 x2 plus c? Because this vector w is nothing but w1 w2, okay? So w transpose becomes w1 and w2, okay? And when you multiply it with, let's say, x1 and x2, okay, so x41, let's say in this case x42, so this becomes w1 x41 plus w2 x42, okay, x42 plus equal to 0, okay? So this was the entire point of taking w x1 and x2 like this, and x4 x5 etc. Okay, so where we were, I think this is 999th time writing, but that's fine. x5 and x6 and x7, all right. So let's say this is x6, x4. Sorry, these don't seem to be parallel, but consider these to be parallel. So, and this is equidistance, right? Doesn't seem so in this diagram, but it actually is. So let's call it as p1, the perpendicular distance of x6 from this line, and let's call it as x p2, okay? So what would be p1? We know the equation of the line is w1 x1 plus w2 x2 plus equal to 0, okay? And what we are also saying is we want the support vector machine to be robust, right? So we are saying this particular line equation of the line crossing through x6 is w1 x6 plus w2 x6 plus c equal to -1, okay? And why is this +1 or -1? As I had shown, right, we want it to be robust. We could have taken at any arbitrary number as well, but just to keep matter simple and consistent, we are saying that this particular number, right, should be 1 or -1 as the case is. And then similarly w1 x4 plus w2, sorry, x61, it would be x62 plus equal to 0, x41 plus w2 x62 plus equal to 1, okay? This is nothing but this is p1, sorry, this is the equation of the line passing through support vector machine x6, support vector x6, and this is support so x6, equation of the line passing through x6, equation of the line passing through x4, okay, x4. So the perpendicular distance p1 is from x6 x4, sorry, so it would be x41, okay, w2 x42 plus c divided by underscore w1 square plus w2 square, okay? And we know this is equal to +1, so this becomes 1 by underscore w1 square plus w2 square. You could write it as to be 1 by, okay, this is what it is, okay? Now similarly p2 would be same thing, w1 x61 plus w2 x62 plus c, and we know that it is equal to -1, but when we take the mod of it, it becomes 1. So it would be again the same thing by w, okay? So essentially we want to maximize p1 by plus p2, which is nothing but 2 by w, right? We want to maximize this, but the thing is we also have few constraints, okay? Sorry, I didn't know what I do. Oops. Okay, I created another page. All right. Yeah, so as you see, I'm also learning over here how to navigate this. Yeah, so this is an unconstrained condition. No, this is not exactly the unconstrained condition, because we will impose a condition over here such that we actually get what we want. Now let's look at this thing, okay? Okay, let's talk about x6. Let's talk about x6 for the moment, x6 and then x7. So we know w1 x61 plus w2 x62 plus equal to 1. This is something which we know. Now if we multiply it with the label of x6, which is again +1, so +1 into +1 is also +1. Now take the consider case of x7 over here, okay? Now the label of x7 is +1, so we write +1. If I replace the value of x7 in place of x61, so it would be w1 x71 plus w2 x72 plus c again. But if you look into this, this would be slightly greater than 1 because this is beyond it, right? So it would be greater than 1. So plus 1 into something greater than 1 again would be greater than 1 only, right? So this is one case for the positive thing. Now let's look at x6. So this is our classification point, right? This is x6 and this is x7. The same thing over here. The only difference being over here, if you write w1 x, sorry, x4 x5, sorry, this was my bad, this is x4. So for this, just imagine that this was x4, so this would be x41, not x61, right? So it would be, let's write it as x41 and then is x42 because we are talking about positive points, right? So therefore it should have been x4. Thanks for your patience, I know. And similarly over here it would be x51, x6, x52, okay? So if we talk about x61, so it would be x61 plus w2 x62 plus c, and we know this to be negative 1, okay? So this is negative 1, and if you multiply it with its label, what was its label? Its label was minus 1, right? Because we are saying it is on the other side of the decision boundary. So minus 1 into minus 1 becomes 1, right? So we observe that, and again similarly for the further point, that is x7, if you put this value x w71 plus w2 x72 plus c, right? So we know that this is on the negative side, right, beyond x6. So this would still be negative, a larger value to negative. It won't be minus 1, it would be minus 5, minus 6, something like this. Now again, if you multiply it with the corresponding level which is minus 1, it also becomes positive, right? So in essence, what we are saying is we can generalize it to be w1 x1, okay, w2 x2, okay, plus c, right? This would be always greater or equal to 1. We have already proved this, right? This is what we are saying, and over here you could write xi. No, this is fine, this is fine, yeah. So this is what we are saying, that okay, xi1 we should be writing, and then we should be writing xi2, okay. So for any point I, if we do this, and I showed to you for the x4, x5, x6, x7, if you do this, yi this plus c is equal to 1. So what we eventually have, we want to maximize 2 by this given yi w1 xi1 plus w2 i2 plus c minus 1 greater or equal to 0. This is what we want to do. So the corresponding Lagranges to that would be, so first of all, maximize 2 by omega, which is equivalent to writing minimize 1 by 2 omega square, okay. And why we are doing it w square, because see, this is in denominator, right? Maximizing 1 by something is equivalent to minimizing the numerator part of that, right? So maximize 1 by w is same as minimize w, right? So this is what we are doing. So we would be minimizing it, given this condition, okay. So the corresponding Lagranges to that is, oh my god, this is what it is coming from. Okay, so we write is minimize Lagranges, we would write it as half of w square minus alpha I, will put it into summation, I is equal to whatever the number of points is, and this is the equation, right? So we just write it as it is. Alright, so this is what the Lagrange's is, right? So this is the condition which I showed to you. Minimize 1 by 2 w square, because we wanted maximization of w, 2 by w, 2 of mod of w, and then this is coming from this condition, right? So I showed to you that for whatever the case is, this stands true, the yi into w1 xi1 etc., right? So this is what we have. Now what we'll do is, see, there are a couple of variables over here. So first is w, the second is c, right? C is a constant, but in this case this is a variable, in the sense that we don't really know the value of c, whatever that is, then it would become a constant. And the other thing is alpha. Alpha also seems to be a variable. So let's do this. Let's differentiate this guy with dw. Okay, so what do we get? This becomes w. That was the trick. Now if you look into this, alpha I this, so this would be alpha I yi into xi1. Okay, all right, so this is what becomes the other thing. Yeah, so this is when you differentiate it with respect to the dw1, right? So it would be this, right, minus this alpha yx, and then it would be equal to 0. Okay, and then we differentiate it with respect to w2, you will get something like the same thing, minus alpha I y I x I2, okay, equal to 0. One thing, so over here when I'm writing w2 square, it would be w1 and this would be w2. Why? Because w square can be written as w1 square plus w2 square. Okay, and when you differentiate it with respect to this, we get this. So generally we can say, and dl by dw, if we are writing in the vector form, it would be w minus alpha I yi into xi. Okay, this is what we could say, equal to 0, which means w equal to alpha I yi into xi. Okay, this is one notation which we get. Now let's do one thing. Now let's also differentiate it with respect to dc. Okay, so this term is a constant, so this would go away, and what would be left is alpha I yi, because this term w1 w2 etc would contribute nothing, and then we will eventually be left with c, and then it would alpha I yi c, so it would become summation of alpha I yi. Okay, c is was there, so if you differentiate, let's say c, then dy dc equal to 0, which means that summation of alpha I into yi equal to 0, right? Okay, good. Now other thing is, why should we also differentiate with alpha? But the thing is, this alpha, there are many, right? It's not a single value. For each corresponding point, you have different alpha. So if you differentiate it, what we'll get is this thing. The alpha I, so we'll just get this point. Wi, w1 xi1 plus w2 xi2 plus c, right? Equal to 0. So which is, if you equate it to 0, it would become equal to 1, but again that would correspond to support vector, right? So we are not really getting something, anything out of it. So we don't really differentiate with respect to alpha, because this points us to a very specific case of support vectors, right? So we just let it as it is. So we get this particular amount, right? So let's just do this. Let's just delete this. Let me get more room for myself. Oops, my laptop seems to have got stuck. Okay, I would need some more space, so it's better that I get some room. Alright, so now let's come over here. Let's write what the Lagrange was. The Lagrange was half of w square, okay, minus summation of alpha, okay, that's I, summation of alpha I, and then it was yi, okay, and then it was w1. So I think in transform, okay, let's write it like this. Xi, we could write that like this. Okay, let's write it wxi, because then in vector notation we understand that. In full-fledged notation it would be w1 into xi1 plus w2 xi2, but I had shown earlier over here, right? We can condense it and write it as a w into xi, right? And then we write it as plus c, sorry, plus c. Yeah, that's what I was missing. minus 1. Okay. All right. So we could also write it as half of W transpose T, right? Because W omega square is nothing but W transpose T minus alpha I and then yi, and this is I summation. Okay. All right. And then we have W into xi plus c, okay, minus summation of alpha I. Okay. I just expanded it. Now you know what is W. W is nothing but this. Okay, alpha I yi xi. So let me write it over here. W is nothing but summation of what? Alpha I yi xi. So we will write it as alpha I yi xi. Okay, and this I from I to whatever the number of points is. So W transpose T. What is this? This is alpha. Okay, let's call it J yj xj, and we are writing it as j because this is transpose, right? So there are two things which are happening, so we need to transpose this guy also. So this is what? This is j, okay, and then we have w, which is nothing but xi yi xi, okay, is from I. So we can combine this and eventually, so let's write it as transpose of this. Now alpha I, yj, etc. These are just scalars. So even if you transpose that, that really doesn't matter anything. So let's call it as I. Let's call it as j. Okay. So it would be alpha I. Sorry, let's write it alpha j. Alpha j, alpha I. We can bring it over here. We can bring yj into yi over here, and then it is xj transpose into xi. Okay. So this is W transpose W, and then we also have we have this alpha I xi. So let's write summation of alpha I, okay, and then we have what? Yi, and then we have wxi. Okay, so W can be written as, because we already have xi over here, so let's write it as j, okay, alpha j yj xj, okay. Sorry, we have what? Yeah, this is fine. We already had yi, you know, so I'm writing in terms of j, okay, and then plus c. Okay, so this is alpha I yi. We'll write it xi, okay, because it was wi. All right, and then we have plus c, okay, plus c, okay. So this becomes alpha, and again the same summation can be over here, I and then j, then alpha I, alpha j yj xj xi. All right, and then we would also have summation of alpha I yi into c. C can be put over here, right? So, and the thing is, if you look into this, we are derived over here, right? We had said that alpha I yi is equal to 0. Okay, so this becomes 0. So this becomes plus c into 0. So this becomes remove. You can remove this. And the last term which was left is minus of alpha I. So the Lagrange's eventually becomes minus half. Let's call this entity as k. Okay, then let's see what is WTW and what is, can we also find what is this particular term in terms of k. So let's look at these terms. Alpha, these two are summations, which is fine. Then we have alpha j, alpha I, alpha j, alpha I, yi, yj, yj, xji, xj. Yeah, so these are, this is exactly same. So we are left with k plus k. All right, and then what we are left is plus this was already there, and minus of alpha, okay, minus of summation of alpha, okay. So this becomes minus k by 2 plus, sorry, minus divided by 2, and then it was okay. So minus minus would become plus, my bad. So this is over here, so this should be plus I. So plus I, so this becomes summation of this plus alpha I. Okay, so it becomes what? It becomes summation of alpha I minus this large term, which is, let me write it once more, alpha I j. I think we can change it over here, and alpha I, alpha j, y I, y j, x j into x I. Okay, so this is what we have. What we have got after the simplification. This is not the Lagrange's, but this is the equation which we have got, which we need to optimize. Okay, which we need to optimize given that alpha I is greater than equal to 0. Okay, so this particular thing is solved by using quadratic optimizers. There are a couple of quadratic optimizers which are used to solve this, right, because we have xij happening. But one critical thing which we need to observe is, which I can take you through in this session itself, is kkt. So I don't know the full form of that. The idea is, see, we need to have this condition along with meeting this as well, right? So earlier this was the case, no? Let me write it this. It also said that this should also be met, correct? yi into, okay, yi into w transpose xi. Okay, so let's write it as w1 x1 i1 plus w2 x i2 plus c, okay, minus 1 is greater or equal to 0. So this should also be correct, right? This should also be correct. Okay, and alpha I was also there. All right. Okay, so I was telling that over here, right, we solve and get the value of alpha, right, using some quadratic methods. But even when we get the value of alpha, we need to be cognizant of a few things. And what is it? So let's write the Lagranges. It was half of omega square minus, right? We were saying that it should be I alpha I into yi into it was wtxi, okay, and then plus some constant c, okay, and then we are saying that minus 1, okay, we are saying this, right? So we need to be wary of a few things. Now let's say let's call it as half of omega square minus alpha I is equal to 1 alpha I. Let's call this gx, okay, for the timing let's call this gxi for this for a particular point. Now let's look at this for a specific point, okay, if, and we want to minimize this, just remember that we want to minimize this guy. So if let's say a particular condition is there in which gxi is negative, right, gxi is negative, which we don't really want. We want that gx, which is this, should be greater or equal to 0, right? If it is less than 0, then this condition should not be there, in which case, you see, gxi would be negative, and negative would become plus, right? So instead of minimization, it would expand, it would increase. So therefore gxi less than 0 is not acceptable, okay, is not acceptable. Now what if gxi is positive? If gxi is positive and we want to minimize this particular number, in which case what would happen is alpha should be 0, because we want to minimize, okay, we want to minimize this. And if gxi is 0, if gxi is greater than 0, right, so we definitely want this quantity to become 0 such that our value is minimized, in which case alpha becomes 0, right? The second case is, let's say gxi itself is 0, in which case it doesn't really matter, right? So alpha I can be greater than 0 as well, right? Therefore if we combine these two terms, what we get is alpha I gxi, okay, this number, okay, should be 0. All right, this should number be equal to 0, and therefore what we are saying is, while we solve for alpha, and why is this important? This is important because we will solve and get different values of alpha, but this should always satisfy this particular equation. Okay, this should always satisfy this condition, and these values would be optimum for this. So this is the SVM part. I know it has been a marathon session, at least for me it was. I hope you had the patience of going through the entire video. In case you have any questions, just let me know. Thanks.